Welcome. In this session, we'll work through backpropagation with our simple example of an artificial neural network that we designed to handle our two-dimensional exclusive OR problem. This has two neurons in the hidden layer, one neuron in the output layer, and down here we have a comparator between the label and the output so that we can compute the residual term. Let's begin with the input. So the input to this, for this example, is we'll have a one form that is 0.5 and 1, and then this plus 1 is what we always append. So let's write that down as our data. So this will be 0.5 value, and that will go to this neuron and this neuron. This will be the value 1, and that will go to this neuron and this neuron. And then this value of plus 1 will go to this neuron and to this neuron. So we've now taken our data 1 form and we've propagated it into the network. The next thing we do is the weights. So from the weight matrix here, the weights for this neuron will be 0.5, 0.50. So I'll note those inside this drawing. So that's 0.5, 0.50. And for the second neuron, the weights are 1, 1, 1. So that will be 1, 1, 1. This neuron will has one output, and that just goes to the output layer. This will have an output that goes to the output layer, and then we have to append a 1 onto this so that the bias term is handled properly, and this one will go to the output layer. The output layer then has weights which are 0.5, minus 0.5, and 0. So that will be 0.5 minus 0.5, and the bias term at this point of our estimation is 0. So we have to perform a forward computation to find all of our values, and then we'll backpropagate the scale factors. So to do the forward propagation, what we do is, the first thing is we compute the linear response of each of these artificial neurons. So the linear response of this artificial neuron will be 0.5 times 0.5, that's 0.25, 1 times 0.5, that's 0.5, and 1 times 0 is 0. So that means that 2u1 will be 0.75. Over here for neuron 2 in layer 2, this will be 0.5 times 1 plus 1 times 1 plus 1 times 1. So that means that 2u2, its linear response, will be 2.5. Those are the linear responses. Now we have to compute the activation function. So the activation function we'll use is the logistic function. Now I'm not actually going to do these exponentials, okay? I happen to remember what these computations will be. And this term will be, so I'll write that down here, that is 2 phi1, so that's the activation in layer 2 of neuron 1, and that will be approximately 0.68. In the notes we carry many more decimal places, but for this illustration I'll just carry 2 decimal places in most places. Here, the activation of 2.5, that'll be quite large, that'll be pretty close to 1, so that is the activation layer 2 neuron 2, that will be 0.92. So we've now computed those. While we're doing these computations, we know that we're going to have to use the derivatives. So we'll compute the derivatives. So if we take the derivative of the logistic function, that's the function c, and that turns out to be the logistic function times 1 minus the logistic function. So we would take 0.75 times minus 0.68 times minus 0.68, etc. So let's compute this, and this will be, I'll write this over on the side here. That will be the derivative layer 2 neuron 1, and that term will be 0.22. The logistic function here, that will be the derivative layer 2 neuron 2, and that value will be 0.07. So it's quite small. And this term will, the derivative of the constant 1 is of course 0, so I won't bother writing that in. So let's immediately observe that these derivative terms are much smaller than the activation terms. And that is going to be important when we do backpropagation. So now we do the computation for layer 1. And that computation will be a little more complicated. So when I compute that, that'll be 0.5 times 0.22 minus 0.5 times 0.7. So that one, that'll be the linear response at layer 1. Now there's no trailing subscript. So that will be minus 0.12. And then when I do the activation of that, that will turn out to be, so that's pretty close to 0. So that'll be the activation, so that's the output of our network, that will be 0.47. And so that immediately tells me that these settings don't know how to classify this, because the probability is 0.47. That means it could be on one side of the hyperplane, it could be on the other side. It really, this neural network doesn't know how to classify this data observation. And then we're going to need the derivative term, so I'll put that up here. So that'll be the derivative term at layer 1, and that will be 0.25. And for this term, for this observation, the label coming in is 1. So we take 1 minus 0.47, and that means that our residual term is 0.53. So that has finished all of the forward computations. We've taken the data, we've multiplied it by the weights to find the linear response, we've taken the activation function to find the output, and then we've computed the derivative because we know that we're going to need it later on. And we propagate that all through. So that's called forward computation or forward propagation. And that's what we need to do with each observation and label. We have to figure out what the state of the neural network is and what our residual error is. So now what we do is we go backwards. So in going backwards, what we'll do is we'll compute the scale factors, and although in the previous session I wrote them down because that's the way that we had deduced it, here I'll write them backwards in the way that we would actually do the computations. So what does this see? Well, it sees minus r. Okay, so that's the first term that it sees. So that sigma 1, so sigma 1 will be minus 0.53. So that's what this sees. Then that gets multiplied by the derivative of the activation function for these values. And so its scale factor within layer 1 only neuron that we have will be minus 0.13. And that means that we can then take that and we then can compute the gradient term for layer 1. So this isn't really proper math, but it's the way that we can keep track of things. What we do is we take this scale factor and multiply it by the gradient for this neuron. And the gradient for a neuron is the data that it sees. So we multiply that by 0.22, 0.07 plus 1 by that one form, and what we get is a one form which is minus 0.09, minus 0.12, and minus 0.13. And that corresponds pretty well to what we're seeing here, right? So what we're seeing is that this is 0.68, 0.92, 1, we multiply that 0.13 by minus 0.13, and so that's the gradient for our overall objective function. That's the gradient contribution from our output neuron. Next, we move to our hidden layer. And so for our hidden layer, the first thing we have to do is say, what weight, what scale factor does this neuron see? And the scale factor it sees is the scale factor for this, which is minus 0.13, times the weight for that, which is 0.5. So what I'll do is I'll keep my same color because this computation isn't depending on what's happening inside this. This is what's being backpropagated by this neuron. So that means that sigma layer 2 neuron 1, what it sees is this scale factor times that weight, which is minus 0.07. And then what this neuron sees is this scale factor times that weight, which is, so that is sigma 2, and that is, I'll omit the plus sign, as 0.07 because those negatives have canceled. So that completes the computations that we can perform based on the output neuron. So we've taken the residual error, we've backpropagated it using the derivative of the activation function to find the weights that this is seeing, and then we multiply that scale factor, which is our S1, by what this neuron sees as its inputs, which is 0.68, 0.92, and 1, and we get the gradient contribution to our overall network gradient as this. We then, sticking with this neuron, we take its weight and its scale factor, and that's what it's going to backpropagate to these. And it doesn't get backpropagated to a constant because we just never differentiate a constant, right? Now, let's slip up to this layer. So at this layer, that now is S21, and S21 is minus 0.07 times that sigma. So that's a really small number. Now I'll actually go to 3 digits because that's what we need to be able to write this and have them be numerically significant. So that will be minus 0.014. So that's the scale factor for the first hidden neuron. The scale factor for the second hidden neuron is what it sees times its derivative term, and now it's 0.07 times 0.07, so that's 0.0049. So I'll write that as S22 is minus 0.00, I'll just write that as 5 instead of 7 times 7 is 49. I'll just write that as 5. So that is the scale factor for each of these hidden neurons. That means that, so what's the gradient contribution for this neuron? Well, I'll write that as the gradient contribution for layer 2 neuron 1 is what this neuron sees times its scale factor. What it sees is 0.511. The scale factor is minus 0.014. So when I cut that in half, that will, and correct for the sign, that'll be minus 0.006 7, and then that will just be minus 0.014, and then minus 0.014, because that is this scale factor times this, the observation augmented with 1, to compute the gradient contribution for our overall objective function from layer 2, neuron 2. That will be the gradient layer 2, neuron 2, will be this scale factor times the input that it sees. So this is going to be really, really tiny. And that'll be minus 0.002, should be 25, but this was 0.49 anyway, so I'm just rounding. Minus 0.002, this will be positive 0.005 and 0.005. And then the overall gradient that we would pick is we would append gradient 1 and gradient layer 2 neuron 1 and gradient layer 2 neuron 2. So we'd string those together, and then we'd get a 9-entry 1 form, which is exactly what we expect because we have 9 weights in our neural network. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we'll have 9 entries in our 1 forms, and everything will work. So let's make a quick observation here, is that the gradient for layer 1 is on the order of 0.1. So I don't know what learning rate the user will want us to have, but the gradients will be on the order of 0.1. These gradients are on the order of 0.01, and maybe, depending on how you want to read it, maybe even smaller. So the gradients have dropped by an order of magnitude, by a factor of more than 10, when we go from layer 1 to layer 2. What happened there? What's happening is it's the derivative terms for the activation functions. Those are very small numerically, and so those are going to produce a scale factor for the inputs that these neurons are seeing that's very small, and so it's going to really, really shrink down the gradients. So if we have a single learning rate for all of the neurons in the neural network, we can expect that they're going to have very different convergent behavior if we use an algorithm for steepest descent with a fixed step size. So, what have we learned in this lecture? We're now able to rewrite the gradient so that we can perform our computations more efficiently. If we evaluate this new gradient from the left to the right, what we're doing is we're finding the gradient terms beginning with the output layer and then through, in our case, one hidden layer, but as we proceed through multiple hidden layers in a neural network. Forward computation through the network finds the essential values that we need. The gradient directions are just the inputs to each neuron. Backpropagation is what computes the scale factors in a really efficient way. And we observe in our case that these scale factors may be numerically diminished or may become numerically very small because of the derivatives of the logistic function, if that's the activation function that we're using in our neural network.